Okay, let's just review. Since we have gone over that, I will go very fast with you. Right? Concept of magnetic field. Right? Make sure you know there's a way to find in your value of constant. Right? That one. And that one, electronic charge. And there is a syllabus. Right? We are going to try to cover this part today.
Which part?
Okay. Magnetic field is widely used. Electromagnet to lift heavy object in your loudspeaker. Right? Where you convert your alternating current to voice.
Into sound, yeah.
Right? And then Millikan's experiment to determine the charge on the oil drop or the charge on the electron. Then we will study this one, velocity selector, where you got your electric field, magnetic field to select a particular velocity. Right? That is what formula we derive. Then we use in MRI, right, where we want to scan the body, usually the backbone, see whether anything wrong with the backbone. Okay. Magnetic resonance imaging to scan the internal body structure. Concept of magnetic field. Right? Field lines carrying, right? We can show the iron filing. We can show that there's a field around the current carrying conductor by scattering the iron filing on the cardboard. Tap the cardboard and then you can see some pattern there. Just like what we did for a magnet there. Scatter iron filing and then tap the table. Then you'll see the iron filing aligned with the magnetic field. Right? So first thing to remember is magnetic field is either produced by current carrying conductor or by permanent magnet. Right? It's not permanent magnet that give you the field, it's current carrying conductor. Also, two of them. And then right, there's no individual pole. You always will find two pole, north pole and south pole together. You cannot break them up. Right? Opposite pole, they attract. Right? We call it unlike pole. Same pole, we call it like pole, repel. Right? That's just as I said, we can show that there is a magnetic field around it by right? Keeping some iron filing, then tapping the table, bench, or use magnetic compass to plot the magnetic field. And we can draw the field of the magnet. Right? It always starts from the north and end on the south. There's the south there. Right? Remember, it leaves perpendicular at the surface there, enter perpendicular. Never intersect, they never catch each other. Right? Where it is close together, we have a strong field, especially near the pole there. Right? Basically, the line just provide a way of describing the field. That part is stronger, that part is weaker. It doesn't give you magnitude, it gives you a relative comparison of the magnitude only, not actual number. So the number of lines is smaller here, per unit area is smaller here, so it's weaker field at the side there. They are imaginary lines, it's in our head. We cannot even see them. And if you want to find at this point there, where's the direction? It's just a tangent to this curve there. And if we are more interested in uniform field, we show it as parallel line, equal distance apart. How do you know that there's the presence of magnetic field? How do you test it? Right? You can use a bar magnet there, hanging in the air with a string, and then it will align with the Earth's magnetic field. Or we can use a current carrying conductor, right? Either we use a magnet or current carrying conductor. There will be, if there's a field there will be a force on the current carrying conductor. Right? So magnetic field will produce a force on a suspended magnet or current carrying conductor. That's how we detect the presence of magnetic field. Then we must be able to define what is a magnetic field. It's just a region of space where a force is experienced by a current carrying conductor or a magnet. Right? Either one. We can use a magnet to detect the presence of magnetic field, or we can use a current carrying conductor. Both will be affected by the field. A force will act on them. And then I ask you to solve this question. Where is the direction of the field along P and Q? Right? On P is just a tangent to the curve. Follow this arrow. Long Q is towards the south pole. It's a tangent also. Right? Then the field never cross. Right? This one, you produce it, they will look like they are crossing, but it's actually a vector field. Right? This part will go that way. This one will go the other way. Apparently, look like they cross, but they don't. They are vector field, so they use parallelogram rule to find the resultant. So the resultant is vertical. All here will be vertical. Right? All here will be vertical. Where they combine.
Even the upper part also.
Say again.
Even the upper part also, lah. If you put a
Upper part
point
is
there.
just to show you one part only. Right? All this part will be vertical. That's why we draw it. Right? It's a vector field. At a point where the two fields appear to cross, the vectors add up to give a resultant field. That's why we show it this way. Right? They repel each other. They don't cross. Okay, force on moving charge. Right? How to represent the field in 2 dimensions. Right? If you are interested in uniform field, right? Parallel lines, equal distance apart. There's the arrow, the tail, the head. So if it's going into the page, then we show the arrow tail. That's the arrow tail from the cross. Right? If it's a dot, means we are looking at the point here, the head coming out, arrow coming out of page. Okay, so sometimes they may draw it 3 dimension, sometimes maybe 2 dimension. So that is your field going inside. There's a field going inside. There's your charge there. Right? We call it magnetic flux density. That's the intensity or the strength of the field. Magnetic field strength or magnetic flux density. American book tend to call it magnetic field only. Right? That's your moving charge. There's a magnetic field going inside the page. Right? That's the velocity. The charge is moving to the right. So there's the force going up. Right? We will look at how we get the force. Right? There's a charge there in 2 dimensions. The force, this one. There's your V. V is going into the page there. Okay. So the force, right? Usually the B is perpendicular to the velocity. Okay, so in this case, the perpendicular component, if they are all perpendicular, is B, BQB. Where B is perpendicular component of B, perpendicular to velocity. Right? So when the charge there moving perpendicular to this field, then the force is maximum. Okay. Remember your B is a vector. V is also a vector, velocity vector. Q is a scalar, right? Quantity of charge, magnitude of charge. So the charge doesn't have to be perpendicular. Sometimes can be moving at an angle to the field, theta. So in this case, right, we just find this component perpendicular to the field, which is this one here. Okay. So that's the force there, magnitude. So that's your V sine theta, right, perpendicular to the field there. Either you take B perpendicular to V or V perpendicular to B, same thing. Okay, so that is the magnitude if it's at an angle. How to find the direction? You use Fleming's left-hand rule. Make sure you know how to do that. Right, use your left hand. Your left hand. Right, your thumb. Thumb give you the motion. First finger. First finger. Right, the three are perpendicular to each other. Right, three are perpendicular to each other. So the thumb is the motion or the force. First finger is the field. Right, second finger is the current. That's the traditional way of memorizing all that. But as I said, you all young people got your own different way of memorizing it. It's okay. Right? But as one student teach me, McDonald's fried chicken, McDonald's fried chicken. Also can use that. Nothing wrong with that. As long as you have to remember, McDonald's M is for motion, S is for field, C is for current. Or father, mother, mother, father, child. Okay. So when the velocity is at an angle to the field, there's your field, there's your charge. It's moving at a velocity there. So where's the direction of the force? Yeah, where's the direction of the force?
Direction of the force.
Yeah.
So between those three,
That's your field. That's your velocity. So the direction of the force.
the one facing upwards lah.
Facing outwards, is it?
Yeah.
Correct. You just think of this as perpendicular to here. So it has to be either in or out only. Cannot be to the right or cannot be up or down. Right? It must be in or out. So we find the component perpendicular. Right? B perpendicular to velocity is B sine phi or theta. Right? Remember the B perpendicular to V, right? Or this one, perpendicular to this one. Okay, so direction is out of the page. That is our traditional way of doing it. You go to university, usually we don't want to use all that lah. We got so many things to remember, so you prefer to use vector method lah. Right? So important F is Q V times V, not B times V. V cross B. Right? That's a cross product or vector product. And if it's a vector product, it's always sine theta. Right? This is a cross product or vector product. So the order of the vector you use is important. Direction of force, you just use your right hand. Right hand, curl it. Curl from V to B. V to B. Right? Curl from V to B. That one there. And the thumb represent the force. So whatever you use is up to you in the exam. As long as you get the right answer. Thumb gives the direction of force. Right? You curl your B. You curl your finger from moving from V to B, and then there's your thumb. Right hand grip rule. Or right hand curl rule, sorry. Okay, that's for the motion of positive charge. So if the charge is negative, where is the direction of the force?
Check again, sir.
If the charge is negative, this is for positive charge. Right? We have got the direction
Yes.
upwards there. Now, if the
Yes.
force is if the charge is negative, where direction?
Down lah.
Ah,
Down lah.
okay, opposite, that's all. You treat your current as going to the right, right? Treat a positive charge moving in the opposite direction, or the current moving in the opposite direction, so it's downwards, correct? Okay, what happened when the charge is stationary? Right? Just using the formula, learning to understand this formula. When the charge is stationary, what happened? Yeah. In a magnetic field, when the charge is stationary, what will happen?
Nothing will happen.
Stationary, no velocity.
Remain constant.
Remain stationary. Right? No force. V0, no force. Charge remains stationary. Just applying this equation, that's all. Charge move parallel or anti-parallel to the field. What will happen? Will we get deflected?
Yes.
Okay. Parallel means this is 0. Anti-parallel means 180 degrees. So what do you get?
0 lah.
No force. So you continue to move with uniform velocity. It doesn't change direction. Continue with velocity. Motion is perpendicular to the field. This is 90 degrees.
Sine 90. So 1.
So the force is maximum. Right? Force is F is BQV. Force is maximum and perpendicular to velocity and field. Charge is negative. Yeah. Open if the charge is moving charge is negative.
Force downwards.
There is no direction. It means the force is opposite to the positive charge.
Oh.
Direction of motion of the positive charge moving in opposite direction and obtain the direction of the force. Okay. Okay. Since we have got this formula, we will use this formula to define our B. Right? Force we have already defined under Newton's law. Right? Charge we have defined from I equals to Q over T, or Q is IT. Right? Velocity we have defined it in your motion. So now we want to define this B. Right? We make sure that this theta is 90 degrees. Right? Then we use this formula. Take your QV down. The unit, we give you a new unit, Tesla or capital T, or it is actually Newton per Coulomb meter per second. Sorry, I've done something wrong again. Yeah, very careless of me. Right? This is over that one there, so that should be reciprocal of that. So this one should be -1. S should be positive. Or you can simplify it further lah. Right? I think this one they won't test you on unit lah. Unit is your first semester work. Okay.
So can just put 1T only lah.
Yeah, T enough already. Okay, so how to define V? Right? If you want to define V, we put this as 1 Newton, 1 meter per second, 1 Coulomb. So magnetic flux density is the force on unit charge moving with unit velocity perpendicular to the field. Remember, 90 degrees. And then 1 Tesla, this is 1, this must be 1. This must be 1. This must be 1. Unit of magnetic flux density, where the charge is 1 coulomb. Moving with velocity 1 meter per second, perpendicular to the magnetic field, experience of force Newton. Right? Always 90 degrees must be there. Then this is 1, this is 1, this is 1, this will be 1. Okay, definition, nothing much. Just know where you get the formula and memorize it. And okay, motion of charge in magnetic field. Magnetic field is coming out, right? This is an arrow tip there, coming out of the page. Or strength V, charge is Q. V is perpendicular to the field. Where's the direction of the force? Waving left hand rule. Field is coming out. Field is coming out. Right? There's your current or motion of the positive charge. So where's the force? Yeah, there's the current. There's a field coming out. Yep. Where's the direction of the force?
Oh, direction of the force.
Use your finger. Use your finger to find out. You need to know that. Yeah, first finger is here. Thumb is coming out, pointing towards you. So where's the direction of the force?
Upwards.
Downwards. How to be outwards? Left hand rule. Left hand. Yeah. There's your field coming out. There's your current. Yeah. Can or not?
How, sir?
There's your field coming out. This one. This finger coming out. That finger current. So that is your force. Yeah.
Oh, okay.
Okay or not?
Yeah, but the first one is the third finger, right? Not the thumb, right? Sir?
Let me show you. I thought you know all these things already. These are your SPM work. What happened? You forgot your SPM already.
No, sir, you can see my hand, right, sir?
I can't see your hand. I'm just trying to get to the screen there. Yeah, how to get to the screen?
No, can you see my hand, sir?
Let me just get the thing done first. You should be able to understand that already. No need to see your hand.
No,
You know your thumb is coming out of the page there, pointing towards you. The current is moving to the right. The first finger is to the right. That you should know how to read already. How to get that? Get to the main screen. How to get to the main screen? Get to the main screen. Okay. That's your field. Right? Remember that's how your finger can see my hand now.
Yeah.
That's your motion of force.
Yes.
There's your field. There's your current.
Mm.
Your field is coming out. Field is coming out.
Okay.
Right? And your current is going there. Field is coming out. There's your field coming out. There's your current. There's your force going down. There's your SPM work. Okay or not?
Okay.
There's your field coming out. There's your field. There's your velocity or current. There's your force there coming down. These are important things you must know. Can
Can.
you spend some time on it? You'll be doing a lot of questions. You say can, we will try some question. Okay, so you should be able to tell the direction. Right? Direction, and then know the magnitude. This one is memory work. F is BQV. Q is the charge on the right, magnitude of the charge. V is the velocity. Is the magnitude of the force constant? Yeah. Is the magnitude of the force constant?
No.
Why magnitude is not constant?
Magnitude is
Magnitude depends on that one. If your V is constant, the speed is constant, the charge is constant, the field is constant, the force is constant. Yeah. Magnitude of force is constant. Yes. Because the speed is constant. The speed doesn't change. Velocity changes direction. Is the direction of the force constant as the charge move? Right? Direction of force, is it constant?
Direction of.
No.
I not sure I haven't tell the answer yet.
Direction of force is not constant.
Oh.
The speed is constant. No, but it's always perpendicular velocity. These two are always perpendicular to each other as it moves. So is the path parabolic or circular path?
Parabolic.
No. That's your last semester work. If the two is perpendicular, it must be circular. If it's projectile, that is parabolic. Electric field is parabolic. Magnetic field is circular. Right? As long as these two are perpendicular to each other. Okay?
Yeah, how can we circular look like parabolic?
Then it doesn't change the it doesn't affect the velocity, doesn't affect the magnitude because it doesn't accelerate the velocity, but it's perpendicular. So as the charge move, this one will be still perpendicular. Right? So magnetic force equals to centripetal force. So magnetic force, centripetal force, V and V can cancel off. Okay, we have to upgrade in a while. So V and V cancel off. So R is equals to mV or BQ. Okay. Take the R up, take BQ down. Okay with that? Don't memorize. Go to this one. Derive it is fast. It's quite fast to derive. Too many formula to derive. Right? The force does not change the speed of the particle. It's always perpendicular to the velocity. That one. It just changes the direction of velocity. Or another way of saying is, instead of saying the force is perpendicular to velocity, we say the force is always towards the center of the circle. Force is constant in magnitude because the speed is constant. Right? So it's a circular path. So use Fleming's left-hand rule on this side. Where's the direction of the force? Yep. Where's the direction of the force? Where's your field? That's your current. Yeah, that's your field.
Force is going to the right lah.
How can it be going to the right? Right is the field already. That's the velocity. So it must either going in or coming out. That's the other direction. Three different directions.
Coming out, coming out.
So that's your field. That's your
It's
current.
coming out.
Coming out. Coming out or going in?
Coming out.
How can be coming out? That's your field. That's your current or velocity. That's your thumb. It's going in. Yeah? Get your finger right. That's your field there. That's your field there. That's your current there. Yeah, that's your current. That's your field. That's your current. Sorry. Okay. That's your field. That's your current going up. Okay. There's a force going into the page. Can or not? Yep. Can or not? Can or not? Can or not? Play with your finger. Play your left hand rule. You must get it right. This is your SPM work. But nowhere I'm still having problem. Can or not? Can or not?
Yeah, can.
Make sure. Need to know how to do it.
Sure.
Okay. Just now we get the direction of the force. Now we are applying it if it's moving in a magnetic field.
MV square.
That's the velocity. The field is going in. That's the force. Make sure you use your left hand rule and check whether the force is in the right direction. Is that the right direction, the force? For this one? Or that one? Doesn't matter. Yep. Or you can use this one if you want to. You should find the force going upwards there. The field is going in. The current is to the right. Yeah, field is going in. Current is going to the right. So the force is going up. Can? Right? That's your field. Going in. That's your current. That's your current. Right? If you look at this one. Right? And your force going up. Can? Charge moving in a plane perpendicular to magnetic field. Right? This magnetic field is going into the page. Will move in a circular path. Magnetic force playing the role of centripetal force. Direction of the force can get by Fleming's left hand rule. And then to find the radius, right? We use a magnetic force equals centripetal force. Doesn't matter about small q or big Q. It's up to you to choose. Cancel the V, 1V there. Then you get your radius, right? Take the R down, take the BQ down. Okay or not? Can get the direction of the force or not? That's important. That's always the first mark you must get. Cannot get it wrong. Yep, can or not?
Can.
Okay, so you want to choose to remember the momentum sitting on honeybee. Right? Instead of honeybee, the 2E, you just change it to Q, that's all. Okay. Momentum over honeybee. So from this formula, we can see that the radius, right, can be capital R or small r. You can choose. Depends on momentum. Larger momentum, larger radius. If B is larger, R is smaller. Right? If the charge is larger, the radius is also smaller. Right? So momentum of charge increases. That one increases. Circle becomes bigger, larger radius. Magnetic field increases, that one become larger, radius becomes smaller. Okay, make sure you know how to use the formula. Okay, check this one. See whether it's correct or not. As for your positive charge, as for the negative charge, use your left hand rule and check. Is it right? Right? It's either going in or coming out. This is going to the left. The charge is going in, or positive charge. For this negative charge, the current is coming out. So where's the direction of the force? Is it correct or not? For positive charge is going up, for negative charge is going down. Can or not? Can or not?
I'm a bit confused. Which one you want me to do for the positive one or the
Doesn't
negative
matter.
one?
You can do positive one first, and then negative will be just the opposite direction. That's all. If they are the same charge, same magnitude.
So positive means it passed through the magnet. So
Positive means it's going into the page. The field is going to the left.
field is going into the left.
Right? Just that. Difficult to show you. Can or not? Field is going to the left, and then it's going into the page. So the force is upwards there. Yep. Can or not?
Nope.
Yeah. Can, huh? I have to stop already soon, and then start a new Zoom. Go over some example with you before we stop for today. Right? If you have got if you have downloaded the sheet, you can try the example. We will be using the formula.
So you want me to tell you now, like the force goes where, upward or downward, right?
The positive charge, the force should be going upwards there. Can you get the direction?
What
Consider
direction
the
of force or velocity?
direction of velocity is going into the page while the force is deflected
Yeah,
upwards.
so positive means force going upwards lah. Yeah.
Can you get that?
Yes.
Okay, ready. Then negative charge is just downwards. So if they have the same magnitude of charge. Okay, we will stop here. Since our time is up, we will do some example, then we call it for a day. Probably will take another 15 minutes or so.
So what subtopic is this?
This is 16.2.
Okay.
We will do some example, then we'll call it a day. So you can take 5 minutes break if you want to.
Okay.